Hi, my name is Jan Wilczek. Welcome to WolfTalk, a podcast about audio programming. In this podcast, you will learn how to build your career in research or programming related to audio, meet programmers and researchers from all around the world, and learn about the intricacies of sound. Hi everyone, and welcome to the fourth session of the WolfTalk podcast. Today you'll have a special guest who works on the cutting-edge deep learning research related to audio. His name is Alec Wright, and he's a doctoral candidate in Aalto Acoustics Lab of the Aalto University in Espoo, Finland. Alec was the advisor of my master thesis, and I consider myself lucky to have met him. We'll discuss how to apply neural networks to music processing, how audio is different in that regard from other areas, and also how to model virtually analog music devices with deep learning. As usual, you can find all references, people, places, and publications mentioned in the episode in the show notes at thewolfsound.com/talk004. A big thanks to Aalto Acoustics Lab for lending me equipment for recording this podcast. And if you like the podcast so far, please consider leaving it a review on iTunes. Thanks. And now, enjoy. Hi everyone.
Hi.
Hi Alec. Thanks for agreeing on this interview.
That's okay.
Could you introduce yourself to the audience?
Okay, my name is Alec Wright, and I'm a doctoral student here at Aalto University in the Aalto Acoustics Lab.
Okay, and how did you end up here as a PhD student?
Yeah. Well, basically, I was studying my master's degree in Edinburgh in acoustics and music technology, and in the duration of this, I went to an AES conference in Milan, where I met Vesa Välimäki, my current supervisor, and after this I applied to be a PhD student here, and that's basically how I ended up here. Yeah.
Nice. I heard that not everyone who applies gets a position.
Well, I wouldn't know.
And it's also cool that you were able to meet him in person, because that was pre-corona times, I guess.
This was, I suppose, a good 4 years ago now or so. Yeah.
Okay, so you transitioned from then mechanical engineering to audio.
So before I did this master's in Edinburgh, I did study mechanical engineering. And then I had a job that, wasn't well suited to me, shall we say. And I decided to go back to school. And when I was, and that's how I ended up going to Edinburgh. They had a cool program that was, it's the Acoustics and Music Technology degree program. And it's kind of a combination of, I think what appealed to me was it had quite a lot of the finite difference time domain method stuff, which is actually quite common in mechanical engineering, and I had done it on my degree already. Only this is in Stefan Bilbao's research department, where they're applying it to modeling of musical instruments and sometimes room acoustics as well. So I think that was part of the appeal. And yeah, it was really great. We did lots of math, lots of simulating systems, musical systems and instruments. Yeah, so I think it was a good transition.
Yeah, and it also maybe was easy for you because I guess you play a musical instrument as well.
Well, I wouldn't say it was easy, but yeah, I do also play the guitar for a long time now. And that was part of the reason why I was also interested in modeling guitar amplifiers and things like that, because I had been playing around with guitar amplifiers for a long time.
So I think that's a good transition to what your research currently involves.
Okay, so what my research currently involves, I would say the maybe uniting flavor? Is it sort of these machine learning or deep learning methods? Although I suppose what the networks that I'm usually using are not very deep by the standards of deep learning, but basically it's applying these kind of techniques to sort of musical processing problems. For example, like virtual analog modeling, so making nice digital guitar amplifiers that you can just plug straight into your laptop and
Yeah, so you basically take an existing amplifier that may be done using analog.
Yes.
How's it called? Like tube amplifiers?
Yeah,
right?
your vacuum tube
exactly.
amplifiers. Although the techniques, because this is a kind of machine learning approach, the specific, the kind of nice advantages that the specific like topology or type of guitar amplifier shouldn't really matter that much as long as you can record some data. So you just need to record what goes into the amplifier and what goes out of the amplifier, and then you can use that to train your model to kind of simulate the amplifier.
Yeah, and ideally you can then replicate that same model in software so that you don't have to carry around a big amplifier.
That's the promise of digital modeling amplifiers and plugins.
Exactly.
Yeah.
So you were in this numerical processing of and physical modeling. How did you transition from this to deep learning? Like, where did the deep learning interest come from?
Well, I would say it was partly just kind of emerging, or I suppose by that point it had emerged, this trend.
Yeah, but I think in audio, it started to get applied heavily.
I think
non-speech audio.
Yeah, definitely. I think it was around the time when I was doing the masters. It was when this WaveNet paper came out, and so this was kind of the first time I think they'd really synthesized like quite realistic sounding audio completely. In a complete with like a complete deep learning approach, and that was really cool, and I think that was part of it because it seemed like really impressive, and it was kind of this point where you were starting to wonder, what you could do with this kind of methods, and it seemed to be the way that things were going, and I kind of was also attracted to the ideas and the kind of. It was appealing, this idea that you can just record some data about the thing that you're trying to model and then create a model like that.
Yeah, and can you specify any specific challenges that are inherent to audio with deep learning? Because we know that deep learning is widely applied in, for example, images, right?
Yeah.
But then what's the challenge when it comes to audio?
So I would say one challenge is definitely the sort of hard to describe. I would say one challenge is how is to do with the kind of scale of audio. Obviously, audio is usually at a really high sample rate, and usually when you're dealing with audio, you kind of obviously the immediate samples either side are quite important, but then information that's happened maybe thousands of samples ago is also really important, and depending on the task that you're trying to do. But
so like the data is kind of dense.
It's dense, and you need to access information depending on the task. You need to access information that might have happened quite a long time ago in a sequence that you're trying to, which is the audio that you're using. So that's quite challenging. And then the other challenge is that generally the sample rate is quite high again, which also means that models that run, they need to, if you're doing inference with a model that you want to generate, a raw stream of audio, then it needs to operate relatively quickly to be very useful, because it's going to need to, churn out at least 16,000 samples per second. But if you're talking about making plugins for a DAW, then probably a lot more.
Yeah, exactly. So there's this heavy requirement that audio software needs to operate in real time when it's a plugin.
Yeah, and they don't, even just operating in real time is not enough. It should be, it should be very cheap.
Exactly.
People don't want a plugin that's gonna, totally consume their processor.
Exactly, and also the memory, right? Like they want to be able to have 20, 40, 60 plugins at the same time. Yeah, we can just clog the memory.
Yes.
Okay, and would you be able to say, if that's a good question, like where in audio is deep learning particularly useful? So which traditional methods failed to provide as good results or comparable as deep learning?
Well, it depends, I think, on how you measure the results. It certainly seems like in speech and for example, where they had been using, they hadn't really gone to deep. There's a long history in speech of using different kinds of models, and now it seems that really these deep learning models are dominating speech synthesis and recognition. So that's one field where it seems like it's become the state of the art. Otherwise, these sort of techniques are starting to be applied in industry, in the audio plugin industry, although exactly how much is obviously hard to say because we don't know what's going on inside proprietary software.
But no one will say, "Oh yeah, we're using this network architecture."
But I think these kind of data-driven approaches, to my knowledge, they sound as good as I've never heard anything that sounds as realistic. Although that being said, some of these models that sound incredibly realistic are, not maybe the most practical because of their size and computational costs to run.
Yeah. So is there a way that we could somehow optimize for speed and for memory of such networks currently?
To optimize? Yeah,
so can we do something to we have a trained network and can we reduce its size or faster?
There are methods from the kind of broader machine learning literature, usually involving sparsity. So making your model, which has loads of parameters, basically pruning away a lot of these parameters. That's one option. You can usually get rid of actually most of the parameters in your model. And a sparse model will work quite well, and that can give you quite a big speed up and also reduce the memory costs. Otherwise, I think it's basically trying to fit these machine learning methods. So it's kind of sort of going away from deep learning a bit and trying to fit these machine learning methods where you're optimizing your model into the kind of traditional framework. So using a lot of the kind of traditional DSP, filters and nonlinearities, but using kind of machine learning techniques to train the models. Okay.
So to not necessarily generate the audio itself, but more to train parameters of much cheaper models.
Yeah, that's one trend in the research that I think is becoming kind of pronounced recently.
Nice. And could you share maybe, as you do, to my knowledge, a lot of deep learning in audio, how do the data sets look like, and what maybe makes a good data set for a neural network in audio in particular?
I mean, it depends a lot on the task that you're trying to do.
Okay, so let's fix maybe the discussion to virtual analog modeling. So we have an analog device, and we want to now model it so that we can have the exact same behavior, but in software, not in analog electronics.
Yeah. So the main thing is that you need to have, well, not the main thing. Well, you need to have enough data And for our purposes, we found that that's actually not very much. You don't need very much data to model a guitar amplifier, for example.
Yeah, so how much data, like on an order of magnitude?
A minute or a few minutes, usually, in our experience. And then the other thing is you want your data to be representative. If you're considering that this data is like basically the excitation signal for the system that you're trying to model, then you want to make sure that your data kind of elicits all of the behavior or enough of the behavior of the system that you're trying to model. So if you just put in like a sine wave at 80 hertz, it's going to learn, you can train a model to do that really well, but it never saw what happens when you put in someone playing a guitar. So you need to make sure that you kind of cover the sort of the whole frequency range, spectrum, I would say. That's important too.
To get all the possible flavors of the device.
Yeah, exactly. Yeah.
Okay. And maybe on a different note.
Sure.
When you look at what is published right now and what is being worked on right now, as far as you can discuss it, like, would you say that in specifically audio effects community, so not talking about speech at the moment, but audio effects community, is deep learning like widely applied and is gaining more and more popularity, or is there still some like bias towards this, let's say, more traditional methods?
Well, I think what you're seeing at the moment is, there's more papers coming out for audio processing with deep learning, but then also there's been more research coming out where they're kind of fusing what they know from these traditional DSP methods with the kind of optimization approach of deep learning. So that's what I would say is quite common. It's quite common at the moment. That being said, there is also research that's kind of more black box in its approach. But I feel like what seems like a good idea and a good trend to me is to use the knowledge that we do have about these systems to help us kind of design our models. And if you look at a lot of the models we're using, they're not actually that dissimilar to traditional DSP techniques. So we can use that knowledge, but a lot of the models are based on convolutional filters, which are obviously widely used in already, and we understand a lot about those, as well as IIR filters and nonlinearities. Those are kind of the building blocks of pretty much all of these machine learning models. So in one sense, it's a black box, but also the model structure is already quite reflective. It already reflects quite well what's used in the traditional DSP kind of techniques.
Okay, so it's good that everything that we learned at the university won't be put to trash.
It wasn't for nothing, no.
Yeah, exactly. And as you mentioned, like convolutional filters, what are the typical neural network architectures that are being used specifically for audio processing? So I guess in the approach we've had for modeling amplifiers, for example, it's either using a sort of WaveNet style network, and what this is essentially these dilated convolutional layers, and followed by nonlinear functions, and just lots of them stacked on top of each other. So that they take like a lot of samples.
So the idea is that it's completely feed forward, which just means that the previous output isn't needed to calculate the next output. It just needs a kind of window of previous samples, which is nice for training because it makes it very parallelizable. Love saying that word. Also it means that it can, the amount of dilation and the number of layers increases how far back in time the model looks when it's predicting the output. And we kind of know from amplifiers and other devices, they do have memory, so they can't predict the output purely based on like the last sample that went in there or the last 10 samples. You need a bit more usually.
Okay. And then apart from this, let's say, WaveNet style models, there are also these long short-term memory, right?
So there's recurrent models as well. So if the WaveNet models look a little bit like FIR filters and memoryless nonlinearities, or Wiener-Hammerstein models, as they're also called, these LSTM, these are recurrent neural network models, and they are sort of, I would say that they're quite an obvious choice if you're dealing with sequences. The whole point is that they have a state, and they're kind of reminiscent of state space models in DSP. And so essentially every step in the input, every sample it takes in, it will update its state, and that state will be carried over to the next time step, and it will use that state vector to then calculate what the output should be for that input. So it has memory in, at each input it only sees directly the current input sample, but it remembers through its state.
So can cover like essentially very, very long.
In theory, in practice, it's not. It doesn't have infinite memory, which It kind of seems like it could, but it doesn't. It doesn't really.
Yeah. Oh yeah, because I wanted to ask you one question, but it escaped me. So, sure. Are there also generative models used? In audio?
So generative models are not something I focus on, but it is a really interesting area that I have been reading about, and. So there's all kinds of generative models. There's obviously the original WaveNet model, which it was intended as a speech synthesizer, but it also did quite a good job of generating quite realistic sounding piano music. But yeah, I would say at the moment the kind of probably the most well-known or largest impact generative model would be this kind of, it's more of a synthesizer, I guess, this DDSP or differentiable digital signal processing architecture, which was basically just based on this idea that you could synthesize, or the kind of autoencoder they created. The idea was that you could synthesize audio through this model of sines plus noise. So you essentially boil it down to a task of creating a bunch of sinusoids and then filtering some noise and adding it together. And if you train a neural network to generate which sinusoids, to determine which sinusoids you're going to generate, their kind of amplitude envelope, and also the filtered noise, like the frequency of the filtered noise. If you train a big enough neural network to control that process, you can make very realistic sounding instruments from data.
Okay, so changing now the topic from deep learning to what you're doing specifically, is that I heard that you have quite many students that you supervise, me included.
Yes. Well, at the moment, I think technically I'm advising, not supervising, but So I have been advising a couple of master's students, and I should have another one coming soon. So
could you maybe tell a little bit what it's like when you start a PhD and now you need to, advise other students, but a while ago you were a master's student yourself?
Yeah, well, it's nice in some respects. I would say it's something that, once you kind of get a bit immersed in the literature and you're trying a few things and you're reading quite a lot, I suppose you have things that you want to try, but you don't really have time to do yourself. So it's quite nice sometimes to have a master's student that you can work with. But yeah, it is definitely, or it was strange at first. I won't lie. But I guess I kind of feel more like with the students I've been working with that we've just been like working together. Not so much that I'm like supervising, that we discuss what you or another student has been doing, and then figure out what you can do next, and what can be done next, and like how to progress. Yeah,
I think it's really cool because like me as a master student, maybe I want to do something, let's say with deep learning, but then I don't know what exactly is needed, what's the knowledge gap, and then you come in that you have like, okay, this will be interesting, this and this, and then you can like pick and choose what to go with and generate ideas for master thesis. So as we touched on this, I wanted to ask you, because when we started collaborating, or you started advising to my master thesis, we needed to do that remotely because of the pandemic.
Yes.
Then could you maybe say what were the challenges that come with this when you need to start a collaboration with someone you don't know at all?
Yeah. Well, I mean, the usual challenges of having only remote meetings, which can be a bit, it's not the nicest way to get to know somebody or talk to somebody. But I would say, all in all, it seemed to work okay. I think the hardest thing about working remotely with people is that it's much harder to, there's always little things. You have a little idea, or you think of you have a comment, and if you're just in the same office, you can just say, "Hey, how about this?" As when you have to organize a meeting or send an email, it kind of loses the whole spontaneity. So I would say that's something that has been much better working in the office as opposed to doing online. Yeah,
I completely agree. And then I'm so glad that I came here, because I think we would have missed out a lot if it wasn't for this in-person contact. I also feel like, from kitchen talk, for example, that new ideas can sprout. Yeah,
definitely. Well, that's the nice thing about being in a lab that's also full of PhD students and postdocs and professors. There's always someone around that you can discuss things with, or conversations that you can join in, and you kind of get a lot of ideas, and you learn a lot like that. You collaborate, and
that's what I also observed, and I think it's pretty cool.
Yeah.
And then for you specifically, when you transitioned to Finland from the UK, how was it?
It was cold. I would say, and well, I was transitioning from Scotland, so it's a bit further north. But it was. I mean, culturally, it's quite different. The language is different, but I think it was okay. The Finnish people, in my experience, have been very welcoming, and the kind of community in the Aalto Acoustics Lab is really good. So I would say there were hard things, but mostly the dark nights, the long dark nights and the cold weather, followed by the extremely long days where you can't go to sleep because it's getting light at 3 a.m.
Yeah, speaking of which, like right now, it's already pretty dark.
It's pretty dark.
It's
been dark since 3, so...
Yeah, exactly. It's getting near to 8 p.m. And I think around 3 p.m. it got dark, so it's already 5 hours.
Yeah.
And we're still in the office.
Still in the office. It's much better when the snow comes. I say that.
And we're expecting that, I think, soon, right?
Who knows?
And about things that are soon to come, can you say maybe a few words about what are your plans for the nearest future?
My plans, well, I have a few publications that I'm working on by myself and also with other people. like my students that I've been working with. And otherwise, I should be, finishing my PhD in the next 18 months or so.
Mm-hmm.
So I will finish that, and then I will weigh up my options and decide where I want to go next. Yeah.
Awesome. So I wish you then all the best with your PhD writing and decisions. And the last question to you is, if someone wanted to reach out to you, where can they find you online?
Well, if you find any of my papers, my email address is there, and you're welcome to send me an email. Also, I mean, GitHub is probably my social media of choice, which is just, github.com/Alec-Wright. Yeah, that's mainly where you can find me online, I would say. I have some repositories up of some of my papers that I've published. You can download and train some guitar amplifier models if you want as well. So
awesome. And I personally recommend reading your papers, because I think for me as a person who started out like in deep learning completely from scratch, your papers actually were a great way to get into it, to see what's the state of the art in this audio effects modeling. And then from these papers, get references to maybe what's worth starting with in a broader sense. So definitely, if someone considers audio effects modeling with deep learning, your papers at the moment are the place to go, in my opinion.
Oh, well, thank you.
So once again, all the best, and thank you for this interview.
Okay, it's been a pleasure.
All right, everyone, that was Alec Wright of the Aalto Acoustics Lab. Thanks again, Alec, for having this conversation with me. If you listeners want to contact him or look up some reference from the episode, you can find all the reference material in the show notes at thewolfsound.com/talk004. If you want to support this podcast, please consider buying a coffee at buymeacoffee.com/Jan Wilczek. And if you would like to stay up to date with WolfSound's publications related to audio programming or audio research, then sign up for WolfSound's newsletter at thewolfsound.com/newsletter. Thanks for tuning in, and see you in the next episode. Take care.